Hi, welcome to Shendra's Engineering Tutorials. It's all about deriving the expression for the stability factor S of a voltage divider bias circuit. Basically, we have four biasing circuits starting from the fixed bias, and having done a small modification in the fixed bias, we go for collector to base bias, and including a resistor in the emitter will give us a feedback that gives us the third biasing circuit. And finally, the most frequently used biasing circuit, voltage divider biasing circuit. This is all to focus on the operating point, so that measures has to be taken that there should not be any change in IC due to change in the reverse saturation current ICO, or a change in VBE, or change in beta. So the question is, when do we come across the problem with the beta? When a transistor is replaced with another transistor, there will be a change in beta, and even that change in beta will give a change in IC, which indirectly shifts the position of the operating point IC value, and that which has there is with that drift in IC value, we cannot get faithful amplification. So we have to design a circuit in such a way that the IC is almost independent of all these three parameters. Why? Because the discussion starts from here. So what is the definition for S? Stability factor S is defined as change in IC due to change in ICO, this one, stability factor S. And in other stability factor S dash, we have change in IC due to change in VBE S dash. And other stability factors comes into the picture, S double dash, which is equal to dou IC by dou beta, in the sense change in IC due to change in beta. Yeah, we have these three stability factors to be discussed. More focus will be on this one. Why? Because a serious problem is encountered when there is a rise in temperature that gives rise to the increase in ICO, still which changes IC. We have an equation showing the relationship between ICO and IC, right? So where to start the analysis from? Not straight away going to that stability to the voltage divider bias and talking about the stability factor S isn't a good idea. No, let's start from the three configurations, and step by step there is a link up from the basic. You have to know, you have to have an idea of what is alpha of a transistor, beta of a transistor. That's enough. No, don't need to go for the third configuration. Basically we have three configurations, isn't it? It's the first configuration, we start from common base. Okay, common base, and we talk about common emitter and common collector. So as far as our discussion is concerned, we can start with the common base and common emitter configuration and some parameters regarding that one. So what is common base? Common base configuration says that if we have a transistor like this one, if you have a transistor like this, like this, like this, guys, what information do I want to give with this picture? I want to say that collector has collector occupies larger place, and base here, if we say it's a emitter, base and collector, base is very thin, right? Collector is large in size, and emitter is in between, the space between base and collector. That's what this picture, what information, this is the information I want to give from this picture. I didn't draw it exactly the center and no equal places. Okay, so base is thinner when compared to collector and emitter has larger area. Emitter occupies larger area in a transistor. And our discussion for, let the discussion be for NPN transistor. NPN transistor. Okay, now this junction, it's a NP, so this junction, it's a JE emitter junction, and this one, it's a JC collector junction, they call it. All right, and guys, what do we mean by this common base configuration? Common base configuration, now the base is common to both input and output. I'll repeat, the base is common to both input and output, and that signal which we want to amplify is given to the emitter, and the amplified signal is collected across the collector. Okay, so that's the meaning for the common emitter configuration. And here, so that signal which we want to amplify is given to the emitter, and output is collected across the collector, right? So I have short circuited. No, wait for the actual completion of the circuit. Guys, remember, to obtain faithful amplification, emitter junction should be forward biased and collector junction to be reverse biased before applying the AC signal, right? Before applying that signal which we want to amplify, we have to make sure that with the help of a DC biasing, the emitter junction is forward biased and the collector junction is reverse biased for faithful amplification, right? Yeah, we have a why that emitter should be forward biased, and we have reasons, but as far as this is concerned, it's only for the derivation part, so focus on these small points, right? Emitter junction should be forward biased and collector junction should be reverse biased. Even if it is a PNP transistor, the same statement doesn't change. The statement is as it is. We have to ensure that emitter junction should be forward biased and collector junction should be reverse biased when the transistor is to be operated in active mode. And active mode, why active mode? Not in saturation, not in cutoff, when the transistor is used as an amplifier. And to achieve faithful amplification, we need to go for this one, biasing arrangement. Okay, so NPN, right? So what should be the terminals over here? N with a negative and positive over this side. Yeah, this is the forward, the junction. Now the junction, emitter junction is forward biased and the collector junction should be reverse biased, right? N with a positive and this one, this negative. Now this is the arrangement. We have to make sure that this happens. We go for this biasing arrangement prior to that applying the AC signal which we want to amplify, right? So this is what, and this negative potential over here, so we'll be having a negative potential over here, right? And this one we have a positive potential over here. So guys, question yourself, with the negative potential over here, what charge carriers experiences repulsion and what charge carriers experience an attraction force? Here with the negative potential over here, we have negative, we have positive, isn't it? It's a negative and this is positive. With the negative potential, electrons are repelled, right? So electrons, for supposing this one, these are the electrons experiencing the repulsion force, right? These are the electrons. Let's say that these electrons are experiencing repulsion force, they enter into the base, which enter into the base. Okay, so these electrons moving the emitter, these electrons moving into the emitter region, that will be IE, emitter current, right? So guys, if the common base, for the common base configuration, now input is given to the emitter and output is collected across the collector. So what will be the input current? It's a guys, now the input current is I and output current is collector current, right? In this case, base is common to both input and output. We are not bothering about the base currents for the time being. Input being the emitter, input current is the, emitter current is the input current and collector current is the output current. So from this one we have a deadly important relationship. Current gain, what is gain? Output by input, isn't it? So as far as common base is concerned, we have a very important factor to be remembered throughout this discussion. Okay, so output is the collector current and input is the emitter current. So from that we have output current is IC upon input current is IE, which says alpha. Common base configuration, the current amplification factor is alpha, right? At times we may be in need of plugging in the value IC is equal to alpha times IE, right? So that's the case. Remember that one. It's very important to which we will be in need of deriving the expression for stability factor, making use of that ratio, right? So this is the case. Now where are we? Yeah, some of the electrons from emitter enter into the base, I mean electrons which are majority charge carriers in the n region enter into the base, right? So base is very thin, very lightly doped with a p region, constructed with a p region. Does that mean don't we have any electrons and holes over here? Yeah, we have holes over here, and electrons also as minority charge carriers in the base. So those electrons which are moving away from emitter, entering into the base region, some of the electrons get recombined with the holes in the base region, right? Some of the electrons, for example, four electrons having started from emitter, one of the electron will be recombined with the hole in the base region, and rest the three electrons will be entering into the collector region. Okay, so this is what practically what happens in a transistor. Okay, so let's suppose I have drawn four electrons. So let's suppose one of the electron got recombined with the hole in the base region, constituting the base IB, base current IB, right? And the leftover electrons which are not recombined in the base region, they enter into the collector, and they constitute the collector current IC. Okay, so this is what it happens. And guys, let this one without this one, let the discussion be carried out without this one. Okay, we don't have this for the time being, but what happens is this potential is enough to do all this action. Just now what I've told you, like because of this negative potential, all electrons will experience the repulsion force, and electron starts moving towards the base, right? So some of the electrons get recombined with the holes in the base region, and whatever electrons are left over, they enter into the collector region, forming the collector current. So what did I say? That IC. And here another important discussion comes. It's electrons are moving in this direction, right? Electrons are moving in this direction. So what will be the hole's direction? The moment of holes, direction of movement of holes, it's against this one, right? So, and if your teacher have told you the transistor, this picture, this arrow indicates the conventional current, not the electron current. Conventional current, the hole current, right? So with that one, yeah, here electrons towards the base, so holes will be base to electron, right? Base to electron. Even over here, electrons are from base to collector, and hole will be coming from collector to base, let's say, right? So in that case, you have from base to emitter are holes, from base to emitter. So we go for the arrow mark indicates the current flow in the circuit on the paper will be indicating conventional current, not the electron current, right? So from that discussion, we make an important conclusion that electrons in this direction, I mean from here this direction, so holes will be in this direction. Even electron this direction, and hole will be in this direction. Okay, so here, and even from here electrons are in this direction, so whole current will be in this direction towards the emitter. And so for that reason, we have conventional current this one, and base current towards this side, and collector currents also this side. So guys, so from this one, they say that the expert says IB, it's a base, isn't it? Now it's the emitter, arrow mark with the emitter, and this is the base, and this is the collector. Okay, so base, we have IB over here, and we have IC, and it's a emitter current, it's a IE over here. Expert says IE is equal to IB plus IC. Alright, so from here it says electrons are moving from emitter to base. In the sense, holes will be moving from base to emitter, and we go for the conventional representation. That's the representation, right? A deadly important relationship. IE, emitter current, is equal to IB plus IC. Check, right? And yeah, we will be in need of this one. We have to plug in we have to make use of this relationship. It may be IE is equal to IB plus IC, or IB is equal to IE minus IC, etc., etc., in the ongoing discussion. Okay, so for the time being, we'll be in need of this one. Okay, so guys, this one, in the absence of this one, so what is that? And what amount of IC is this? What amount of IC? IC is equal to, which is coming from emitter current, isn't it? Here the electrons constitute IE, emitter current, entering into the base, that will be IB, and entering into the collector, that will be IC. So what amount of emitter current has become collector current? It's not 100%. Why? Because emitter, a few of the electrons gets recombined with the holes in the base region, so there is a drop in the quantity of the current moving from emitter to the base, I mean towards the collector. So what amount of emitter current is collector current? It's a alpha IE times, right? This is the one. This amount of emitter current becomes collector current. Guys, check, alpha is always less than unity. You will come across it while solving some problems. Yeah. Beta value, in other configuration, beta value will be very high, but alpha is always less than unity, right? This happens, this current IC is equal to alpha IE because of this forward bias, because of this emitter junction being forward biased, right? And now what about the collector junction? It's a reverse bias junction, isn't it? With the negative and with the positive. Okay, now talking about that biasing condition, that biasing, forget about all these now. We are done with what amount of IE will be IC? Alpha times IE will be IC, right? We have a base over here. In the absence of, when emitter is open with this connection, guys, when emitter is open with this connection, what is this connection? We have a positive potential over here, isn't it? And negative arises over here, for supposing, not supposing, it is. Now it's a base is made up of a p-type material and collector is made up of a n-type material. Okay, even in the absence of this one, right, even in the absence of the forward biased junction, in the absence of forward bias voltage, when the collector junction is reverse biased, holes, guys, because of this negative potential, electrons experiences repulsion due to this negative potential. Underline this very point, electron in the p region constitute the minority current. Electrons, we have a negative potential, isn't it? We have a negative potential, we have a positive potential. Okay, so holes experience repulsion force over here and electrons experience attraction force, isn't it? So with that one, when the electron experiences a repulsion force over here, electron, which is a minority charge carrier in p region, enter into the collector region towards the positive potential, right? And this hole, which is a minority charge carrier in the n region, experiences a repulsion force and that crosses this collector to base. In the sense, in the absence of the forward bias voltage, when the collector junction is reverse biased, a reverse saturation voltage will be also flowing in the collector region, right? And so the total collector current is equal to emitter current this much plus the reverse saturation current due to the reverse bias. In the absence of this one, when emitter is open, they specify emitter is open. Okay, it's collector to base current. It's a collector to base current when emitter is open. ICBO. It's like this one, where it's a collector to base current, collector to base current when emitter is open. It's a reverse saturation current. Here we need this one. This one you have to understand, you have to focus on this one to go to the derivation for the stability factor S, this ratio. Yeah, we have IC, we have ICVO. Right? So guys, this is the total collector current flowing. This is due to the forward biased contribution due to the forward current, and this is due to the reverse saturation current flowing in the collector region. Right? What about the second configuration? In other configuration we have common emitter, isn't it? So common emitter, once again let this be the emitter and this be the base. Once again saying that base is thinner, collector has larger value, and NPN transistor. Now the emitter is common to both input and output. Input is given to the base, and so IB will be the input current over here, and output is collected across the collector, so IC will be the collector current, IC will be the output current in this configuration. IB is the input current for common emitter configuration, and IC is the output current, right? So again another important factor comes into the picture with this assumption. Like, it's not assumption, it's the truth. Like common emitter configuration, IB is the input and IC is the output, collector current is the output. So we have a gain similar to this alpha. We have, what is that output current in this configuration? It's a IC by input current is IB, isn't it? IB. So guys, it's a current gain IC by IB in output current by input current, and the ratio is denoted with beta. The first one was alpha, this one for this configuration, and for common emitter configuration it's a beta. At times we will be in need of plugging in IC is equal to beta IB. Okay, so as far as our discussion, yeah, it's a lengthy, I know, but without having a basic knowledge on this one, it's impossible to I won't be happy if I go straight away we have IC without all these explanations. So I had to go for this one, right? This equation is important. For the time being we don't need this one. Why? Because we have these I could establish this relationship. I need alpha and beta to go for this one. We are in search of stability factor S. So the expression for the stability factor S, and these factors are enough. These stuff is enough for me to derive that expression for stability factor S, right? So what is alpha? Going back to the alpha is equal to, it's a, guys help me, it's a IC by IE, right? Yeah, IC by IE, and from the picture of the transistor it says IE is equal to IB plus IC. So plugging in IC in the numerator, IC as it is, okay, IC as it is, we need to plug in IE, which is equal to IB plus IC from this one, from that previous discussion. Okay, so this is for the alpha. Okay, so taking in, we need an important when we need in alpha in terms of beta, we need to go for this ratio. So how to go for this ratio? Divide, by IB whole by IB. Okay, right? So this gives us IC by IB in IC by IB in the numerator, and this one 1 plus IC by IB, which is equal to, guys, it's alpha on the LHS, IC by IB, it's another important ratio, current gain, IC by, it's a beta, so beta by 1 plus beta, relationship between alpha and beta. We need this one in the derivation, which we are in search of the stability factor, right? Cross multiplying this one, alpha is equal to beta by 1 plus beta. Okay, so cross multiplying this one, what we have is alpha, cross multiplying alpha plus alpha beta, which is equal to beta, all right? So beta, alpha as it is, beta minus alpha beta, which is equal to, taking beta as common, 1 minus alpha and alpha on LHS. So beta will be equal to alpha by 1 minus alpha. Even this is important relationship, right? This one. Alpha is equal to this, beta by 1 plus beta, and beta in terms of alpha, alpha in terms of beta and beta in terms of alpha. Beta is equal to alpha by 1 minus alpha. Okay, so guys, we will be in need of plugging in an important relationship. What is that? So what did we have for beta? So guys, I'm erasing this one. Yeah, this one. Okay, so this is the one we will be in need of. So guys, can we go for beta is equal to this one, right? 1 plus beta is equal to 1 plus alpha by 1 minus alpha. Yeah, we can do it, right? Beta is equal to alpha by 1 minus alpha. I have added 1 on either side. Will that be a problem? No. So simplifying this one, we have 1 minus alpha, and cross multiplying it's 1 minus alpha plus alpha. Alright, so what gets cancelled over here? Negative alpha, positive alpha gets cancelled, and what we have is 1 plus beta is equal to 1 by 1 minus alpha. We will be in need of plugging in this value also in the ongoing discussion, right? So we need this one. Yeah, so guys, we have this one, IC is equal to, again recollecting this one, IC is equal to alpha as it is. IE could be plugged in with IB plus IC from the transistor configurations and the flow of currents, plus ICBO, right? So separating over here and shifting IC to this side, what we have is IC minus alpha IC, which is equal to, we have alpha IB from here, right? What did I do? IC as it is, okay? So we would have alpha IB, which is this, plus alpha IC, I have shifted to LHS, right? Plus ICBO as it is. Now taking out IC as common, what we will have here, 1 from this one minus alpha from here, which is equal to alpha IB plus ICBO, isn't it? We are in search of IC, we need this one, so I need an expression for IC. We need an expression, so we need an expression for IC. So IC will be, right, IC over this side, IC will be equal to alpha by this one, it's multiplying, that side it will be dividing, isn't it? So alpha by 1 minus alpha into IB plus 1 by 1 minus alpha into ICBO, right guys? So what is this? What is this? What is that? It's a beta, isn't it? From the previous knowledge, from the derivation. So IC is equal to beta IB plus, what the hell is this? 1 by 1 minus alpha, 1 by 1 minus alpha, it's a 1 plus beta, so that could be plugged in over there. 1 plus beta, right? ICBO. Guys, we have to start from this equation for the stability factor. I could have come directly to this one, but I'm not happy. We need to have, for a beginner, you need to have the fundamentals of all these, so I had to do this derivation, all this derivation, right? Stability factor, the analysis stability factor starts from here, right? So guys, ICBO in the case of the first configuration, and ICEO in the case of second configuration. Generally it's a ICO, yeah, right, in general. So guys, it's enough. We had this one, we need this expression, so I had to do, okay, I need this place, right? And there is a small change in the I forgot to tell you something. The exact expression for the stability factor, you may be by now, you might have started trolling me in the comment. Please, it's a stability factor S is dou S, okay, S, it's not S dash, S, dou IC by dou ICO, that one. This I erase this one B, because ICBO in case of common base configuration, ICEO in common emitter configuration. In common, it's a ICO, the reverse saturation current, right? So here, when the other two parameters, what, VBE comma beta, are constants, right? So guys, coming back to this expression, what do we have, guys? Differentiating the entire expression with respect to IC, the first derivative of IC of this expression. So here, dou IC by, dou by, what do you say in mathematics? It's IC is equal to beta IB plus 1 plus beta ICO, isn't it? So what we go for is dou by dou IC of this one, it's a constant, right? So dou IB by dou IC, right? And it's a dou by dou IC, right? So what is this? It's a 1, and what else? It's a positive this side. We are in search of this one, isn't it? Yeah, we have S over here. S, it's in reverse, right? And here it's a positive this side. Shifting to LHS, that will be negative beta dou IB by dou IC, which is equal to 1 plus beta. What is this? According to the definition, dou ICO by dou IC. No, S is dou IC by dou ICO. It's a 1 by S. It's a into 1 by S. So that expression for S is from here. S will be equal to cross this side, this comes this side, and the entire this term goes that side. So what we have, 1 plus beta as it is, nothing to do with this, 1 plus beta by 1 minus beta dou IB by dou IC. Okay, so the very general expression for the stability factor. Making use of this one, all the four configurations of 4 different biasing arrangements. When we go in search of the stability factor, we evaluate the expression for IB, and simply the first derivative of that equation with respect to IC will be having dou IB by dou IC. Just straight away plugging in that one, 1 plus beta by we will go in search of this one in whatever circuit we are exercising on to derive the expression for the stability factor, right? So this is the general expression, right? Yeah, where did we start from? From alpha and beta and relationship between alpha and beta, right? And the relationship between the 3 currents in the transistor, I is equal to IB plus IC whole current, right? And from that one we plugged in, we somehow reached to this one. This equation gives us the expression for stability factor S. S is equal to 1 plus beta. What did I do over here? The whole part is brought to this side. S is shifted to that side, right? So in that case, S is equal to 1 plus beta as it is. This comes down 1 minus beta by, no, it's not by, 1 minus beta into dou IB by dou IC, right? So this one, making use of this expression, we can straight away obtain the equation for the stability factor of any 4 of the biasing circuits, right? So I need this one. So guys, it's, what did I say? Stability factor S. Now this one, now we have this one, stability factor S for a voltage divider bias with all these with this equation. With this equation we can go, we have to draw the picture of the voltage divider bias circuit, right? Voltage divider bias circuit, and then we can derive the expression for the stability factor S, right? How the voltage divider from the transistor, from we have to start from the transistor here, very precisely we have to draw this. Here we have base, and this arrow mark to say that precisely, to say that it's a emitter E for the time being, E, and this is the base part, base terminal, and this is the collector terminal C, isn't it? So guys, biasing, they say biasing, isn't it? So biasing with these resistors provide the required biasing. They give the name collector resistor to the collector, isn't it? So RC, and we have another resistance over here, it's a RE, right? And to this voltage divider, isn't it? Now this divides the voltage divider R1. Here it's a nerve R1, and R2 divides the VCC plus VCC. This divides, potential divider rule, yeah, that divides the voltage. So voltage divider, the name voltage divider from this arrangement R1 and R2, isn't it? So here guys, remember another important point to be noted down in capital letters. Yeah, you will have questions from voltage divider bias. Another name, we have another name for this one. You go in search of that one. Yeah. While deriving the expression for the stability factor, or while designing a self bias, I repeat, while deriving the expression for the stability factor, or you will have a numerical, you will be given a numerical to design a self bias for meeting some specifications. You have to obtain the values of R1 and R2, RE, something like that. Even in the numerical part, you have to obtain the Thevenin's equivalent of this circuit. That is into rocket science again. Remember, you have to somehow, you will be struck at a point, right? You may forget that you have to reduce the circuit to its Thevenin's equivalent. Reducing the Thevenin's equivalent will help you to go ahead in a numerical where you are struck. Yeah, you have to, this equation, this circuit should be reduced to its Thevenin's equivalent, right? So how to reduce that Thevenin's equivalent, guys? This part as it is, okay? Now the Thevenin's equivalent over this side. What is that? The transistor part as it is, with the base over here, and RC also, even this RC as it is, okay? No change in the RC here with the collector, and even no change in RE, okay? So no change in that one, and yeah, there is a change over here, here. I repeated this as it is, okay, right? And with the ground over here, the ground. Now what is that voltage which we have between base and emitter over here, this side? What is that voltage? It's the voltage, let's say it's R2, isn't it? So that voltage appearing over here, let it be V2. What is that V2? According to the potential divider rule, we have V2 is given as R2 into the supply VCC by the total resistance R1 plus R2. Now this one will be our VTH, Thevenin's voltage, right? So we have a Thevenin's voltage with a negative and a positive with the ground. Now this is VTH. This is the value. What value of VTH? It's VCC into R2 by R1 plus R2, right? And Thevenin's voltage, and we should have a Thevenin's resistance in series with the voltage, isn't it? So according to Thevenin's rule. So how to obtain that one, guys? We don't need this anymore. Short circuit this one, short it with respect to base, okay? With respect to base, when we short it, with respect to base, now it's like as if this R1 and R2 is connected in this side, and R1 and R2 is connected in this side too. It's parallel. It's with respect to base, R1 and R2 are in parallel, removing the DC voltage. So RTH will be over this side. Can I go? This is for VTH, and RTH is equal to the parallel combination of R1 and R2. That's a R1 into R2 by R1 plus R2. The parallel combination of R1 and R2 with respect to the base. With respect to the base. So what is that? Now this one will be the RTH. With respect to the base, isn't it? So we have RTH over here. RTH, which is equal to RB as suggested by the experts, right? And with respect to base, the close it, and now it's a closed circuit. Now this is the, we have plus VCC from the previous one. Now this part, output part is as it is, input part is reduced, input, basis, input is given to the base, isn't it? So with respect to the input part, we reduce this initial circuit to its Thevenin's to for simplification, right? And from here, again we have to consider the currents. What current flows into the base? It's a IB. And what current flows over here? It's a IE, isn't it? So starting from here, this drop, now this will be the supply to the input loop, including, I mean this one, this supply, this voltage drop is equal to this drop plus, guys, I'm very sorry, we need to have this one, we need to have VBE. How can we forget it? No, we cannot forget it. No, that's important. Very sorry, I was in a hurry to explain this one, so I didn't mention that one. Very sorry. We need to have VBE between base and emitter. Even that creates some problems while in biasing arrangement, right? VTH is equal to this supply is equal to this drop plus this drop plus this drop. How to write that one? VTH is equal to VTH is equal to how to write this one? It's a IB and RB. RB is RTH once again. RTH is parallel combination of R1 and R2 with respect to the base. Okay, plus VBE plus, how to write this drop? It's a IB plus IC into RE. Hold on, I just plugged in the value of IE is equal to IB plus IC. That's it. IE has got nothing to do as far as this discussion is concerned. Wherever we find IE, that could be plugged in with this one, because we need dou IB by dou IC. So IC is valid, IB is valid. IE has got nothing to do in this expression, in this part, right? So for that reason, so VTH will be equal to IB into RB plus RB from here, and IB into RE plus RE from that term. Okay, so plus VBE plus IC into RE. Hope this is clear, right? IB is coming from this and this, so IB has come out from this and this, so RB from here and RE from here plus VBE plus IC RE from here, right? Now we are there, we are almost over here. So here with this expression we don't need this anymore. Okay, with that expression, this one, remember VTH is equal to this one, R2 into VCC by R1 plus R2, and RTH is the parallel combination of R1 and R2. DC is short circuited, and with respect to the base is still holding R1 and R2 on either side, right? So with respect to base, and so RTH is given to the base, right? And over here VTH, it's a constant. You will understand this is a constant, that VCC will be equal to 12 volts or 15 volts like that, 5 volts like that, isn't it? It's a constant. So the first derivative of the entire expression with respect to IC, dou by dou IC of VTH, which is a constant, that will be 0, which is equal to RB plus RE into dou IB by dou IC plus VBE is a 0.3 volts or 0.7 volts, like that. It's a constant value, even that becomes 0, plus dou by dou IC of RE as it is, RE. So dou by dou IC of IC, that's 1, isn't it? We need this value because we have to plug in over here. Okay, so that gives us into, isn't it? So dou IB by dou IC, that will be, it's a positive, now this side that becomes negative, by this one. I'm shifting this to this side. Okay, so it's a plus RE, this side is minus RE, and we need only this one, so this is multiplying, that divides this side, RB by RE. Okay, so that's the expression for dou IB by dou IC. So plugging in this over here gives us the expression for the stability factor S of a voltage divider bias circuit. So what is that expression for S? It's a 1 plus beta by 1. This negative and this negative constitutes positive into plus beta. Dou IB by dou IC is here, RE by RB plus RE. Expression for the stability factor of a voltage divider bias circuit. Right? So guys, remember, for the fixed bias circuit, it's simply 1 plus beta. Now this value is divided by this much quantity. Something is divided with this value. So there is reduction in the stability. It's a betterment. This says it's a betterment. Okay. So this is not all. We have to go ahead. We have to, by maintaining some condition, the stability factor could be, we can obtain a betterment in the stability factor. That can be shown like this one. It's like guys, over here, let this be, S is equal to, let the 1 plus beta be as it is ahead, let it be like thoda sa, I mean I've just shifted it away, right, by, guys, we have a by 1, right? So simplifying this one, cross multiplying this one, what do we have? It's once again we'll have a ratio in the denominator, isn't it? So in the denominator we're going to have a ratio, and the denominator of the denominator, RB plus RE over here, isn't it? Cross multiplying, what do we have? It's a RB plus RE plus beta RE, right? Guys, I cannot go for another step. This, I mean, we have 1 over here, this goes up, isn't it? So this goes up. What is that? It's a RB plus RE goes up. This one, this is the simplification, isn't it? So guys, what if we take S, okay, change the color for you to understand, 1 plus beta as it is, and RE as common from all the terms, from here, RE, okay, RE as common from all the terms. What do we have? It's a 1 plus 1 from here, 1 plus RB by RE, RB by RE from here, okay, and what else? RE as common in the denominator also, that gives us 1 from here, 1 plus beta from here, beta plus RB by RE, RB by RE. So guys, make a note of this one, this simplification. I'll be erasing this one. Now what gets cancelled? This RE gets cancelled, and I mean this RE, right? So we don't have that anymore. So if we could have a design, if we could select the values of RE in such a way that if RB, the ratio RB by RE is very less than 1, in the sense if RB is very less than RE, I mean that one, that relationship, sorry, right, or else RE much greater than RB. If that is the case, if we could decide, if we could select the values of resistances in such a way that this, if this condition meets, now this ratio will be very small. Yeah, that ratio will be very small. And with this condition, guys, with this condition, by selecting the value of RE in such a way that RE is very much larger than the Thevenin's resistance, the parallel combination of R1 and R2, what happens is this has got no significance. Why? Because this ratio will be very small when compared to 1. I mean, this will be very much less than, like the design, less than 1. This has got no significance. Okay, now even this ratio has got no significance, right? I'm erasing this away. Okay, I'm erasing this away here. This got cancelled previously itself, and with this arrangement, if the values are like this one, this has got no significance, and even this has got no significance over here. Okay, so guys, what are we left with? What are we left with? It's this one, and something else gets cancelled, 1 plus beta and 1 plus, so S will be approximately equal to 1, which is the best design. Stability factor S is equal to 1 is the best design. So with what condition that is done? With this condition, by selecting the value of RE like that, this one, you got to prove this one, right? And yeah, this is important, we have to reach to this one. With that assumption, with that selection, we can go for this one, guys. Another important relationship has to come into the picture, which will be very helpful while solving the numerical. What is that? So guys, going back again to this one, what did we have? Taking out RE as common, remember S is equal to 1 plus beta we had as it is. Okay, so taking out RE as common, we'll be having 1 plus RB by RE in the numerator. RE got cancelled, isn't it? So again, RE got cancelled, and what do we have? 1 plus beta, from here RE came out, plus RB by RE it is. Remember this one? So guys, a small simplification, S is equal to multiplying this one, 1 plus RB by RE as it is for this one, plus beta RB by RE. Why? Because this into this, I mean this into this plus this into this, that give us this one, beta into this, beta plus beta into this one, right? And 1 plus beta plus RB by RE from the previous one. Okay, so guys, I need this place, and what do we have from here, guys? Cross multiplying this one, S plus beta S, cross multiplying this into this, plus RB by RE into S plus, okay, plus what else do we have? What plus? What am I talking? Which is equal to 1 plus RB by RE plus beta plus beta RB by RE. Guys, RB by RE terms on one side, and the rest of the terms on either side. So S, it's independent of RB by RE, so I have written this one, plus beta S, and even this one, it's a positive, it will be -1 over this side, so we don't have this anymore, isn't it? And even this one, it's a plus beta, it will be minus beta this side, so we don't have this anymore. Okay, it's a positive, which is equal to Guys, RB by RE as common from this and this, right? So RB as common from, so from here it will be 1 plus beta. It's a positive this side, to that side it will be negative, and RB, taking out RB as common, that will be minus S. And over this side, a small simplification over here, it's a S from here and here. What do we have? S, and S has come out 1 plus beta. Okay, close the bracket. Minus 1 is common from here and here. What do we have? 1 plus beta, right? Which is equal to that one. So here S minus 1 into 1 plus beta, which is equal to RB by RE. It's multiplying, that coming this side it will be dividing, 1 plus beta minus S. Guys, believe me, an important relationship, RB by RE, that comes into the picture, that will be very helpful while in designing a self-bias circuit, I mean voltage divider bias circuit, right? So hope you understood the analysis. We started from the relationship alpha beta, and finally what was proved? That what did we have? S is equal to 1 plus beta by 1 plus beta RE by RB plus RE, right? That was proved. And what else? Yeah, with some assumption, with that assumption, S will be approaching 1, which is the best design for the stability factor with respect to change in ICO, and this ratio RB by RE, S minus 1, this will be helpful. So hope you understood the analysis. Guys, support me with your valuable share and a subscription. It's very valuable for me. Thank you for watching.